write what is
Cn minus 2 and Cn minus 1.
2. The Cn minus 1 goes all the way, so it is product of Pj from 0 to n minus 1. Cn is up to n minus 1.
Cn minus 2.
Okay. So product of Pj from j from 0 to n minus 2 is what we have here. Okay. That into bn minus 2. And the same thing here. Here you have up to the previous one. And then a bn minus 2 square. Just write it down and you see they cancel. Okay. This is the product of bj's up to n minus 2. So this is bn minus 2 square and the product of bj up to n minus 1. And this is what the product of bj up to n. So these things cancel. And so what you get is only this term, which is Cn minus 1 into bn minus 1, which is Cn. Okay. This is this term. Okay. These terms cancel. So you get Cn. Okay. Now we are ready to prove theorem. All this Pn and get of 0 are monic orthogonal polynomials for the distribution of A for the pure state. The projection on P. So these Pn's are nothing but orthogonal polynomials. For the distribution we are interested in, they mean the distribution of A over this pure state. So what do I mean by that? The Pn should be a polynomial of degree n, and monic, that means the leading coefficient should be 1, and they should be mutual orthogonal. The distinct one should be orthogonal. So first things are easy. So clearly Pn has degree n. That is the way we define it. Right? P0 is 1 and Pn is the determinant, the characteristic polynomial. Yeah? So clearly degree of Pn equal to n, and Pn is monic. That means the leading coefficient is 1. Okay, so that part is easy. So other thing I need to show is that for different m and n, they are orthogonal. That is the expectation of the product is 0.
Sir, by orthogonal product you mean for the vector space of the corresponding distribution, right?
Yes, exactly. Exactly. So they are mutually orthogonal, corresponding means distinct ones. So
PMA, PMA.
yeah, Pm, if I have a distribution, Pmx, Pnx, the integral d mu. Okay, so that should be 0 for n not equal to n.
They are real polynomials?
They are all real,
Yeah.
right? Because we have made
Matrices are
all the matrices are real. Okay, and though that should not really matter. They are real. For m not equal to n, this is 0. Or in other words, I want to say the expectation of Pm into Pn is 0 for m not equal to n.
My question was that measure is the distribution of A, right?
Yeah, distribution of A on the pure state UU. Okay. So integral is nothing but the expectation. Right? Integral of x p mu is the expectation of x. The integral of pmx is the expectation of pm. So I want to compute this expectation of u on pma pn. Okay. So m and okay. So m comma n greater than or equal to 0. So m not equal to n. But this is u pma pna. This is just some polynomial in A. So the expectation is you just apply it on A and take inner product with you. Apply it on U, take inner product with you. And that is the expectation by our definition. But U is same as E0. Okay. That is the starting vector. Okay. But these are real polynomials. Okay, so PMA is again self-adjoint, so I can take it to the other side. So this would be PMA P0 times inner product with PNA P0. That you know it is some constant Cm times Em, some constant Cn times En. Right? This we have shown the previous lemma, which is hidden now. So the CM, CN for some constant CM and CN, but they are orthonormal. Right? So this is 0 or some not equal to n. Okay. Because the previous lemma said that this is equal to some CN A is 0 is CN A. So they are orthonormal. Okay. So in fact, I can get orthonormal polynomials by just dividing by the norm. Because if I take m equal to n here, I will get Cn square. Okay, so if I just divide by that, so take Qnx equal to Pnx divided by Cn. Again, they are non-zero because all our Pj's are non-zero. Cj is non-zero. Okay. They are all non-zero. So that means Qn and greater than or equal to 0 are orthonormal polynomials. Now no longer monic because I have divided by Cn. So this recurrence relation then is the recurrence relation for the orthogonal polynomials. Okay. Because Pn's are monic orthogonal polynomials for distribution. So these things are well known that orthogonal polynomials have this recurrence relation and this kind of things. The three-term recurrence relation. We just got it from the matrix theorem. Well known. Okay, so with every self-adjoint operator, we have got a thing like this. Okay, so let me make two comments about these assumptions now. What these assumptions meant. Okay, the first one. I took linearly independent so that in the Gram-Schmidt when I divide it is not 0. So if you don't have that, that means it terminates at certain stage. Like some a to the power n u belongs to the span of the previous things. Okay. Then if you apply a again, it will again be in the span of that. Right? A to the power n u is in this span. If you apply a again, it will again be in this span. So that means u, au, etc. a to the power n minus 1 u, it is left invariant by a. Okay? So a is self-adjoint. So if a space is left invariant, it is also means its orthogonal complement is also left invariant. It's left invariant by a star also. So that means if I take this subspace, okay? If I suppose this is the case, then I just take the things up to that. Okay? So that space, if I call as K, the whole space H decomposes as K direct sum K per. Okay? What matters is only this part, because A gives that invariant, and all I do is take powers of A, apply on U, take inner product with them. Okay? So on this, the A breaks up as some A0 here, like this. And what matters for us, the distribution of A on the pure state, only this A0, because that space is left invariant. Okay? So you reduce yourself to this matrix, right? Some matrix of certain size, so up to n minus 1, so n cos n matrix. So you get a smaller matrix and you are studying that. Okay, so that would mean when you look at this tridiagonal things, it is just a matrix. The whole process terminates at this stage. Okay, and you just have some n cos n tridiagonal matrix, and you are looking at its distribution. So all the other analysis up to that you can do. Even subsequent to that also you can do. No problem. But so the distribution is concentrated on the eigenvalues of that n cos n matrix. Okay, you have a distribution with just a few masses. Okay, so it is finite dimension. So that is what happens if the first one, assumption 1 fails. Means you truncate it and you got a matrix. How the finite dimensional things are described by that. If A is finite dimensional, or if this span becomes linearly dependent of some state, then it reduces to finite dimensional analysis. Okay, but otherwise it is okay. You get a tridiagonal matrix of certain n cos n size, and you go only up to that. Yeah. Okay. What about the second one? The second one is also similar. If the span closure is not whole of H, that span closure you call as K. The rest as K per. The rest doesn't matter, because the whole analysis is only on that K. Right? The distribution of A just depends on K. Okay. So that also you just break it up like this. So just to take K as span of this, span closure of this. So the effect this works for both the cases. Okay. So it doesn't matter.
Without loss of generating current.
Yes. Okay, and this. Okay, there are many examples. Maybe one wait because the time is up. So, but let me just put down one example. Other examples maybe next time. I'll put this one, the diagonal 0, and it's half everywhere else. Say half times this matrix. The diagonal 0, everywhere else here 1. In this case, you can compute all the moments. Okay. It's a nice exercise to compute the moments. See, the first moment is anyway 0, right? Then you take the square and the cube and things like that, and if you see this, so I want to compute the nth moment like this. Okay. U is the E0 to the power n. Now this one, if you see, forget this half. It's half to the power something will come when you take nth power. This is each step you go one step above or one step below. That kind of thing, right? Here in this matrix, E of En is En minus 1 plus En plus 1. Right? One step back or one step forward. So you can compute, and you want to compute the thing b to the power some k comes back to 0. step above or one step below each time, and you come back to it. Okay? And you are not allowed to go below the horizontal axis. So there are paths like this. From 0, you want to come back to 0, like this or this. Each time you go one up or one below and come back to 0. How many paths are there? Say of length 2k. If it's odd, you see the paths, there is no path. And if it's even, how many paths are there? So that is, you can compute. This is 0 if n is odd. And the number of paths if you compute, so Catalan numbers. The number of paths. Yeah. So I can nice exercise. 2k plus k divided by k plus 1 will be the number of paths. But I had this half sitting outside, so the power of that will come out. So you can compute the moments, you can compute the orthogonal polynomials. So they are, so maybe I will write down everything next time. So they are known as Chebyshev polynomials of second kind, and the distribution itself, this is a random variable which has a density, and a well-known density. The density is 2 by pi square root of 1 minus square for mod x greater than or equal to 1. So f of x is this, and 0 otherwise. So it's a density which is just concentrated on minus 1 to 1. Up to a constant is a circle, so semicircle. So it's called Wigner's law or Wigner's semicircle law. And everything is described by this matrix. The distribution of this on this pure state is Wigner's semicircle. So next, maybe I will write down this kind of tridiagonals. You can write down the tridiagonals for all the densities, all the distributions, the standard distributions. You have the semicircle, normal, Poisson. For everything one can compute. People have computed these orthogonal polynomials. So you know the coefficients. These coefficients an and bn of the Jacobi parameters are well known for most of the distributions. So you can just write down as to what are these matrices.